Welcome to another AIP Zoom into Physics. I'll start by acknowledging the traditional custodians on the land on which we're all meeting here. I'm in DY in New South Wales, so for me it's the Darug Nation, and I pay my respects to their elders, past, present, and emerging, and a particular welcome to any Indigenous people here this evening. Tonight is the topic is the future of power. If you've been to these sessions before, you'll know that we choose something fairly weird and wonderful, not connected with the previous one. We have a list of about 30 topics that we've brainstormed. Not all of them are suitable, but there's some weird and wacky ones there. And we were talking before about what we might do next time, and thinking maybe what is mass or what is matter. That was getting some really good conversation going before we started. So we're talking about the future of power. We've got a few topics, we've got a few experts, and what I'll do to begin with is get our regular panel and our guests to introduce themselves, and as they do so, just to say who they are and what they do, and what if they had a choice, what is the technology that they would choose to be the one that would solve our future power needs, and why? So let's kick off with the regular crew, and maybe I'll open up to you first, Tibor.
Thank you. Yes, I'm Tibor Molnar. I'm a philosopher of science. I'm an associate at the University of Sydney, and my favourite power source is going to be the sun. It's going to go on for billions of years. It doesn't do anything to the Earth. We get plenty of it. We get about 10,000 times as much energy from the sun as we consume today. So there's plenty of it around. And I think it's non-polluting, it's harmless. We should exploit it. And I think that's enough to meet our needs forever. Well, for another 4.5 billion years.
Thank you, Tibor. Let's go over to Kirilee.
Hi, so I'm Kirilee. I'm the experimentalist here. So I am a neutron scatterer, and I work for ANSTO, which is the Australian Nuclear Science and Technology Organisation. So even though I work for a nuclear science and technology organisation, I think that going on into a long-term future, I'm backing the same thing as Tibor, as you can see behind me. I think solar is the way to go. It's limitless. There's a lot of improvements happening in solar cells and organic solar cells actually at the moment. I would like to have a shout out to this picture behind me. Does anyone know where it's been taken, by the way? Anyone recognize it? No, it's a new solar farm.
Is it one in Broken Hill?
No, it's the one at Tullamarine. So at Melbourne Airport, during COVID, they decided, all right, there's no flights. Let's see what we can do with the big paddocks around Tullamarine. So they've built this solar farm here to try and service the terminal buildings at Melbourne Airport. So yeah, like Tibor, I think that, there's still some limitations. There's still some challenges to be answered. There's still efficiency that we need to combat. But going into the future, for clean energy, for our environment, solar's the way for me.
Thanks, Kirilee. And Geraint, I know Geraint's going to say something different, but over to you, Geraint.
I'm gonna say two things if I can. So firstly, I start with agreeing with both Tibor and Kirilee here. One of the things, I should point out, I'm a cosmologist and I'm at the University of Sydney. And one of the areas of my research is thinking about the long-term future of the universe. And if we're talking about the real future, the real future, if we are ever going to become a civilization that travels between the stars, then it has to be solar. I mean, solar energy, for starlight is the cheapest energy source that we have in the universe. And of course, we've had people speculating for many decades now about harvesting not only the light that would land on the surface of the Earth, but the light you could harvest if you had spacecraft, going all the way ultimately to these devices known as Dyson spheres, which capture the entire output of an individual star. But the thing that I have in the back of my mind, which really bothers me about, the real long-term future, is that our universe is awash with energy, right? We know that currently 70% of the universe is in the form of this stuff called dark energy, which is causing the expansion to accelerate. And we just do not know yet if we can ever tap that energy source. But if we could, then that is the truly limitless energy source that we have in the universe, because eventually the stars will die, but dark energy is one of those things that will go on forever.
Okay, thank you.
Fair enough.
Let me introduce one of our special guests tonight, Warren McKenzie. Warren is the managing director of an energy company called HB11 or HB11?
11.
11, okay. Tell us a little bit about that, Warren.
Well, it's the commercial embodiment of a fusion reaction and a fusion approach that was born and bred in Australia. So not many people know that Sir Mark Oliphant, one of the people who discovered fusion energy, discovered the proton-boron reaction, as it's otherwise called, pioneered by one of our third co-founder, or Jan, who's in the audience here. We also have Professor Heinrich Borer. He pioneered the development of it over a very, very long time. And it's exciting now because there's been a bunch of experimental results showing that it works a whole lot better than anyone ever imagined, and also proves that the thermal approaches to fusion that everyone's been pushing for a very long time is not the only way to demonstrate fusion. So that's HB11. Me personally, I'm a material scientist. I'm academic at UNSW, still in the School of Material Science there. I had a silly idea that some scientists have of doing a business degree, and since then have started a string of companies. And HB11 will be my third. The others are still running, importantly. So that's me. Oh, my favorite power source. I have to do one up on each of you there. I know power from the stars is very, very important, but I have to say fusion, not just because it's my job, but fusion is where the power comes from all of the stars. Okay,
thank you. We're expecting Patrick Hartley. There's a couple of things which just say iPad here, so I'll just ask if Patrick has arrived yet. No, okay. Patrick Hartley is with CSIRO, the same organization that I'm with, and he's the leader of the hydrogen industry mission. So if he joins us a little bit later, hopefully he will be able to talk to us about hydrogen, which has been a lot of talk about recently. So what we aim to do with these events is they're very informal chats, as you can gauge. We love it when people really get involved, and it's a free-flowing discussion. Everyone's welcome to voice their opinions or ask questions. So please don't feel shy in just interjecting, and in a respectful and constructive way, of course. But please do get involved. This is really just a bit of fun, really, on a Wednesday evening. So with that, let's kick off. We physicists, we love to define things. So let's define power. It's often called energy. That's probably not correct, or is it? So maybe panelists, what's power?
Do you want the physics answer?
Any answer? Well, this is a physics session, so physics is permitted.
Yeah, well, power is the energy delivered over time, basically, right? So you have a total amount of energy, which we can measure in a whole bunch of units, but physicists prefer joules. And that energy could arrive quickly, or that energy could arrive slowly. And the rate that energy is delivered is the thing we call power. So joules per second.
Oh, Tibor, unmute.
Yes, I was going to ask the obvious question then. What is energy?
Energy, well, am I going to be the physics definition dictionary?
Well, you mentioned it, so I thought I'll throw it back at you.
Well, energy is the stuff that allows work to be done. That's
okay, yeah, not bad.
See, I have to interject here. This is what I tell all of my students. I say that energy is everything. Everything is energy. So time is energy. If something arrives after a long time, then it's got low energy. If it gets there quickly, it's fast. If something has temperature, then it's energy. So we can, I would define everything in the universe as having energy. Or perhaps the measure of energy is probably a more a better description of the way I describe things in the universe.
Okay, so what if I then said that energy is the measure of motion? It's a measure of how things move or how much things move. If nothing's moving, we would say there's no energy around.
except for potential energy.
Sorry?
Except for potential energy.
Well, okay, now that's an interesting question. I asked Brian Schmidt this question. I asked him what is potential energy. And he looked at me rather blankly. He said, I've got no idea. The reason
that's what happens when you ask a Nobel Prize winner, right? You have to ask a real physicist.
Oh, very good.
Hey.
Very good. No, his answer was that if energy has anything to do with motion, if potential energy is stored motion, then he doesn't understand what stored motion is, because he doesn't know how you store motion without moving. So he had a difficulty with it. He said he thinks, and I'm inclined to agree with him, that potential energy is just an accounting tool that helps us account for the conservation of energy rules that we like to make up.
Yeah, well, yeah, yes, at some level, but it's energy to do with the configuration, right? So it's positions and velocities are the things that how you define the energy of a system.
Yeah, that's right. It's the energy of the system that you're not measuring because you're measuring the energy of the system. It's the energy of the rest of the system. It's the energy which is not actually available to you. It's available to some system that makes it move. I think it's something like that.
Peter Green has got his hand up there. I don't know if you can see his little hand. Did you have something to say, Peter?
I think he might have put it in the chat. Mass is condensed potential energy from E plus MC squared.
I think that's meant to be E equals.
Oh, E equals, beg your pardon, yes.
Yeah, okay, yep. Mm-hmm.
Okay.
But I think this comes back to one of those things that I can give you a formal definition of energy. I can write down the equations, but you know, energy is a bit like that definition of pornography, right? You know it when you see it. It can have a very rigorous definition, or it can have a more flexible definition, and it depends which one you want to work with here.
Can I throw gravitational waves in the arguments here? Surely there's energy in them, but that's not motion, right?
Oh, it is a motion. It's a waving motion, isn't it?
So what's waving?
Space-time, if Einstein would define it.
Oh dear, we could end up again having a fight over definitions here. So yep. I mean, the big question of transmitting energy via things like gravitational waves and via electromagnetic waves, the question of whether or not the thing carrying the waves actually carries the energy is a question for the philosophers rather than the physicists, because you can talk about the energy at the source and the energy at where the thing is received, but is there energy being carried between A and B is a much different question.
Well, wouldn't you have to interpose? You could stand in the middle halfway between the two and find out.
But then you're the thing that's interacting with the
wave.
Yeah,
then you've disrupted it. Once you've measured it, you've disrupted it.
That's right.
But I think waves are energy. You know, again, short wavelengths, long wavelengths, they tell you the degree of energy.
Yep, I think that's right. So it is still a measure of motion, isn't it?
Absolutely.
I'm going to disagree, but I think we should probably move on.
Good. Let's say joules and watts.
Joules and watts, yeah.
Joules and watts.
Are we happy
Okay.
with that? Brilliant.
Yeah. Okay. Good. So what we're really about here is providing watts for the nation, for the world, as in joules per second. Interestingly, total human power consumption is around 160,000 terawatt hours per year. So there's a lot of energy that we've got to find per unit time. So let's have a discussion about the what are the various options that we have, and then we'll dive into some of them and talk about some of them in detail, and perhaps some of the associated issues that we might have. So let's just have a sort of a brain dump of all of the different sources that are available to us. What's out there?
Well, obviously coal is out there.
Coal,
we don't
yes.
want it to be out there, but it's obviously the highest, one of the highest used resources. Coal, oil, natural gas. They're the top three, aren't they?
Let me yeah.
So obviously the cons of using those are there's a limit to them. When I was trying to look at it online, coal, we've only got about 100 years left of coal. Natural gas, less than 50 years, and oil around 50 years. So, you know, there's a real strong limit to using these resources. And the second issue, which is probably the more pressing issue, is the environmental impact of using these with their carbon footprint. So yeah, let's put a big X on these ones.
Okay, I've got another little poll here, which sort of answers the question, but will hopefully stimulate some chat. And I'll run this poll twice, once now and again at the end, just to see whether I think it'll be interesting to see whether this discussion has changed minds. For some reason, I'm not allowed to vote. I think I guess there's nothing stopping me logging in on a separate screen and doing that. You might have noticed on the previous poll that I put the ACT twice. That's because I didn't put it at all last time. So I thought I'd better redeem myself. But there's no one from the ACT here at all this time.
Well, no one that would own up to it.
No, that's right. And for any people who are AIP members, my apologies to Geraint. I said Geraint Thomas in the email that I did out at the weekend. I knew I was going to do this, so I mentioned I was going to do that, I think back in November. It took me this long to do it, but anyone who's a cycling fan will recognize the name Geraint Lewis. He's a cycling star. And sorry?
You mean Geraint Thomas is a cycling star?
I know. I must apologize to Geraint Thomas now. Hopefully it'll be in the Tour de France. It's going to kick off, but maybe it's going to be in the Olympics. Anyway, we're off topic. Sorry. Has Patrick arrived? No, I don't think
Seems
so.
not.
Okay, so biofuels are definitely out. Fossil fuels are definitely. I'll end the polling and share the results. It seems that more than half of you reckon solar is the way to go. That's
we
good.
must have been very convincing in our
yeah.
opening statements. Yes.
So, what other areas are worth a mention that anyone would like to discuss?
Are we able to jump in with the odd question?
Please
Yes.
do, absolutely.
Because on that poll, fusion is so exciting, and I guess this is for Warren particularly, but it's been put to me, even with all these breakthroughs and this, ITER and all these other things going on, that the economics will take a long time to be attractive. It'll be like the early fission power plants when we get them started, the cost per megawatt. whereas photovoltaics are kind of running ahead on this cost curve. They're just so good. And so do you think it'll be a long time before fusion catches up with the economics of solar to be more attractive, even when we get them going?
Well, I think, you look at some of the big fusion reactor projects around the world, not us, we're certainly not one of the big ones. I mean, they've pumped billions into those, into what are the most complex machines in the world. And they're getting more complicated, every time you ask. How can you make them, firstly, how can you stop the projects when you have whole generations of scientists who know nothing other than these fusion approaches? But it's absolutely right. I mean, we've had investors ask us for what's our techno-economic model, which is a polite way of saying, can you show that you're actually going to make money at the end of the day if you, if you generate the reactor? And that's honestly something that we're looking into. I think probably going a little bit beyond the economics, which the economics obviously is a huge thing that the world needs to look into, and particularly for the mainstream fusion, so the thermal fusion approaches, where their big issue is they have to hit these ridiculously high temperatures, hundreds of millions of degrees. And of course, when you heat something up, you have radiation losses. So, you're losing a lot of heat, or certainly a lot of energy beyond just the complexity of the machine that is there. But one of the other points is with thermal fusion, the reaction of choice is deuterium-tritium. Not many of the nuclear crew say that tritium's an awfully nasty thing. It has to be bred. It's awful. You can store it. I think they typically use it as a gas. I think the amount of tritium that's going to be needed to start some of the big future tokamak projects is in the tons, or at least in the order of tons, and the total world supply of tritium, I think, is in the kilos. So, no one's considered the economics of where you're going to get the tritium from and how you're going to breed it and how much that's going to cost, because it's not been demonstrated. I guess plugging us a little bit, one of the big differences that we have is that we're a non-thermal fusion approach. So going back through the history of what I touched on just in the introduction, the entire world has been obsessed with thermal fusion, basically trying to replicate what happens on the sun for a very, very long time to create that deuterium-tritium reaction, through compression and heat and all the rest. But the thrust of what we're doing is essentially what our third founder, Professor Heinrich Thor, predicted as far back as the 60s, that maybe there's a way that you could do fusion without temperature, without thermal equilibrium, as it said. And that's interesting, because if we were to do hydrogen boron fusion with very, very high temperatures, you'd need billions of degrees. It's just not going to work. I mean, no one's making 100 million degree reactors work. You're definitely not going to make billion degree reactors work. But what was nice out of that is, this thermal approach, which is using high power lasers as essentially ion accelerators, and then smashing hydrogen and boron into each other, was the result. So what's on our side, I guess, if you go back to the half a decade, the idea that you could have petawatt lasers, some of the most powerful things in the world, where you have a very, very intense pulse that you can use to very efficiently accelerate ions, just wasn't heard of. What we know now is that the development of these lasers has outpaced the development of semiconductors into these incredibly powerful lasers, which, is, I guess, going back to where we are today. The last couple of years, there's been a few experimental demonstrations of what Professor Thor predicted in the 60s as a result of this work in lasers. So going back to the question about the economics, in my opinion, it's our company. We expect that we don't have any of the issues associated with thermal fusion, so we are more likely to have something economically viable. Where that sits relative to solar is going to be a function of how we're doing the science, right? We're about 4 orders of magnitude away from net energy gain. We don't know whether our science project could get us to 5 orders of magnitude, we're just over the line, or 8 or 9 orders of magnitude where the world's energy problems are solved. That's a science project. That's the exciting part about it. So the short answer is we don't know.
Maybe can I add something from this perspective as well about the economics? I mean, when you see these economics of solar, you say 1 or 2 cents per kilowatt hour. That's nice, but it's not everyone in the world is blessed as Australia with a lot of sun. So you have to also take into account it's not always available, right? So you have to these 2 or 3 cents, you have to add the cost of more transmission, the cost of storage. So that's really to compare something that is always available to something that is sometimes available in some places of the world more than others. So that's something that needs to be taken into account for economics as well. So so I guess that's one of the most people don't really do this. It's a bit sad, I think. So look at the whole picture, not only at one thing. And you always have this. I mean, you can see it, the famous solar duck curve in California. It's a lot of solar is available during the day when the air conditionings are running, but during the evenings and late afternoon when everyone still wants to keep the air conditioning running, they switch over to gas because that's the only thing they have. And I mean, I think battery storage is maybe another topic for the future, but I'm not seeing that it's going to be a terawatt hour level of storage that would be needed for some countries in batteries. I mean, that's just my opinion.
Yeah, that's absolutely right. You know, I think that there's a real lag in the capacity and the cycling of batteries at the moment in terms of storage. So people who build new houses here in Australia at the moment are being advised to put solar panels on their roofs, but they're not being advised to add the batteries because the batteries haven't reached the efficiency yet or the lifespan that makes them cost effective. And again, it's all, you know, you talk about cost and cost effective. You put solar cells on your roof, and how long until you start to break even? Is it 5 years? Is it 10 years? One other thing I wanted to point out with economics, especially with a startup company like what Warren is talking about, a lot of money is invested in the science. This is not money down the drain. It's money that is furthering, you know, humankind's knowledge. It's, you know, developing spin-off companies. It's developing different technologies as well. So there's a certain richness in pushing the science and investing the money in a company like Warren's talking about. I just read up about it this week, and I think it's absolutely fascinating what you're doing at the moment, Warren.
Thanks.
And Jan.
So let's dwell on that for a little bit. Can you give us the short 5-10 minute spiel of what a laser boron reactor is?
All right. So basically, we use these very high peak power lasers. So think of these. Well, probably the best description I can give of what these lasers are. You imagine if you shine a laser at the moon, right? For 1 second, that's about how long the laser beam takes to stretch from your laser pointer to the moon. Imagine if you've got quite a powerful one of those, but you could compress that into the distance of about a meter. Suddenly you've got a very, very high peak power of high power of laser energy in a very, very short pulse. So where the physics of this progressed was basically, well, this can be used for ion acceleration. And for the ANSTO people and accelerator enthusiasts around, I will go as far as to say this technology of being able to accelerate particles is probably going to put a lot of accelerators in the world out of business because these are much, much more efficient ways of accelerating ions. Anyway, essentially, moving on to the non-thermal fusion. So for those who are not familiar with fusion, thermal fusion, we have atoms very hot moving around. Hopefully they'll bump into one another. Essentially what we're doing is well, technically speaking, it's non-thermal equilibrium fusion. You got a proton here. We use a laser to shoot, a boron atom here. You use a laser to shoot a proton at it. And there's a probability that that proton will hit the nucleus of the boron and you'll get a fusion event. So essentially, we're not using, we're using the very efficient high peak power lasers to create a very, very big, like I guess we've called it plasma block acceleration, where you have a huge amount of these protons flying through a sample, and that kicks off a fusion reaction. Some of the exciting parts of this is, you know, a lot of physicists will say, okay, beam fusion, you know, you bang an atom into another one, you're going to get fusion. Sure, so what? Who cares? The point, probably one of the critical points is some of the experiments that have been done have shown reaction rates much higher than can be explained by regular beam fusion. Now there's a lot of debate in the scientific community about how and why, but one of the key perspectives which is published is that there is a chain reaction going on. So you have you know, the proton plus the boron creates 3 alpha particles, so no neutrons, which means it's a safe reaction, which is one of the nice things about it. The alpha particles that are produced, or the helium nuclei, go and hit another proton or another boron, accelerate those to create another, the secondary fusion reactions, and it creates some manner of chain reaction. So that is a means of amplifying the amount of this reaction, and basically gives us hope that this fusion approach could get, you know, we could eventually get more energy out than we pump into it. The other, I guess, 2 elements, and I think this is where it very nicely ties into the discussion about hydrogen, is this is the only fusion approach, certainly that's being pursued, that can create electricity as a product of the reaction. So unlike all of the other fusion approaches that are producing temperature with their tokamaks or whatever else, they're trying to heat water to turn a steam turbine to generate electricity. Because the proton boron fusion reaction creates this explosion of high energy alpha particles, their motion against an electric field and their charge neutralization can create electricity directly. Now, going back to the techno-economics of all of this, we still have to design a reactor that's going to turn that into something useful. And of course, the obvious choice is, okay, we try and turn that into grid electricity that we pump into the grid, and then people can use whenever they want, because it's not intermittent. That's great. But certainly looking into Alan Finkel's climate technology strategy, well, I must admit I was a little bit critical of it myself, because, you know, hydrogen isn't a source of energy, it's a means of transporting energy. Where does the energy come from? It's a very good from the perspective of if you consider where the world's carbon emissions come from. And they don't all come from the grid. There's only about 1/4 of the world's carbon emissions come from the grid. So, you know, you can talk about electric cars. So yeah, maybe electricity can replace the automotive, but quite frankly, I mean, you know, the vision of Kirilee's background of littering the desert with solar panels and using those to create hydrogen is actually a nice one in an Australian context. From an Australian context, as Jan said, it saves the intermission issue and means you can put it into cars. But I guess the same applies for us. If we're a nuclear approach that can directly create charge, why can't we apply that to electrolysis applications? So the 2 big electrolysis applications are aluminium smelting and water splitting for hydrogen production. I'm looking, you know, doing economic stuff at the moment, and I've got a report on my desk that says, you know, we got to replace 100 million barrels of oil per day. That's a lot of solar cells to split water. Maybe you need a nuclear approach to do that.
Warren, a quick question. If you're generating electricity directly from your boron hydrogen interaction, you'd be generating DC, not AC. How would you, well, you can put that through an inverter, I know it's not a problem, but how do you control for voltage and all the other things? How do you make it usable power rather than just getting an awful lot of electrical energy coming out of it?
That's a question that I'm in the process of hitting Scott and his colleagues at CSIRO's High Voltage Lab up about. I can't call myself a high power engineer, but I know there are technologies out there to do that. I know, sorry, I sound like a politician for avoiding the question.
No, but I mean, it's right. I mean, we have these intense pulses like every few a few hundred or even 1,000 a second, and we have to turn this somehow into a stable supply. So there's quite a few ideas. I mean, even going to like having a huge spinning flywheel, like going back to the rotational mass that a large coal or a gas plant has, because I mean, sure, we have to stabilize this output somehow. But again, like, yeah, I have to agree with Warren. the high power engineers have to come up with something.
But I think the point that I'm making about the hydrogen versus grid power, any company in developing any products, you have to start with a minimum viable product. You can't try and go straight to market with the optimized Ferrari. You have to go to market with the first thing that you can try and sell. For us, the energy conversion for something where you put an electrode in that may not be that sensitive to voltage, probably going to be a whole lot easier, attaching it to an electrode than it will be producing nice 50 hertz AC.
Okay. Yep.
And what about the economics of the fuel? I mean, how much is it going to cost to get all of the whatever it consumes, the boron?
Well, boron is abundant, isn't it?
Yeah, if I were at home, I have an IKEA coffee cup that costs about $1. So that's a typical high temperature glass. Back of the envelope, that's about 10% boron. The high temperature glasses are full of boron. And of the isotope that we need, which is boron 11, that's 80% of the boron which is found. So we're hoping we don't need to get rid of the rest of the boron in there and do any purification. But if all goes well and we get good reaction gains, this may be a matter of digging up a few milligrams, shooting a few milligrams of boron that really hasn't had much processing beyond digging it up out of the ground. But quite frankly, exactly what that looks like, we don't know yet.
Right. But like Tibor said, it's easily obtainable. It's an open pit mining, so it's like digging out sand out of the big hole. So it's not a problem.
Maybe I'll rephrase the question. Well, where are the big costs in that? And is this a plant the size of a nuclear power plant, or is it in the back of a truck? Give us an idea of what it might look like.
So that's going to be again a function of G. Our big goal is G. Do we get G to 1 or do we get G to 10? If G is 10, we're probably going to need a very big laser. Talking $1 billion. There's the Laboratory for Laser Energetics, which hopefully in University of Rochester looks like a football field. Those lasers, because they pump 30 kilojoules into through a sample in sub nanoseconds. Now, if it's depending on where the physics lands, and honestly we don't know that, we're getting really good results with 100 joule lasers, and those are in the millions of dollars and can be pulsed at 10 per second. My gut feel, if we land there, this is potentially something that you'd have in your backyard, or it would be modular to the effect that you might have a 1 or a 10 megawatt system in a shipping container, and if you want more energy, you buy more shipping containers. So the short answer is we don't exactly know. The biggest power and the biggest technology that is going to be in this is going to be in the laser. And what's been working in our favor for decades now is that laser technology has been moving faster than semiconductors.
How far down the road are you? Have you managed to get it off the paper and actually do the experiment and blast hydrogen into boron and produce something and prove the concept?
I'm not allowed to say because we have to publish results, but we have a very good result.
Okay.
Yeah. I'd love to say more.
We'd love to hear more. Maybe offline.
Yeah.
Soon.
Yeah. Can you buy me some drinks for that?
Yeah.
I don't have
A couple
wine
of beers and we'll get through. Yep.
But yeah, we have exciting results that will be very well publicized, in hopefully around September, October time.
Wow.
Okay. Good.
And are you the only company that's pursuing this at the moment?
There is sorry, my email's just going off. There is another company that's trying something very similar to us. Other than that, and they're a startup. And they, that's, from our perspective, we see that as imitation is the best form of flattery. Beyond that, so one of the big companies, TAE Energy, so TAE stands for Tri-Alpha Energy. They've been pushing out the same reaction, but from a thermal approach. So they're a very, very big company, raised upward of $1 billion. I don't remember the exact figure, which have generally been
800 million.
Yeah, I guess converted to Australian, it's probably about that. But they're going down the thermal approach. They've got some big infrastructure. They haven't gone down the same path of the non-thermal fusion that we're pushing. That said, there are a lot of research groups getting really excited about it at the moment. So, no doubt we'll have some competition popping up.
So on a related topic, we hear a lot of, well, not so much recently, but a few years ago, there was a lot of hype about the thorium cycle. And again, I believe that uses a laser as a spark plug. Is that does anyone know how that thing's going? Is that a viable thing?
I think that's a replacement for fission, right?
Yes, fission. Yeah,
Yes, fission.
That's right.
So I don't think it has anything to do with lasers. It's just a different material that you can split. But to be honest, I really never understood what the big surprise should be. And I mean, it's a heavy element, and so it's pretty much the same.
Essentially, it's
uranium.
more abundant, right? So the thorium's more abundant than the uranium-235. So
and maybe it is also like the weapons square issues are not as big because you don't breed plutonium, right?
well,
So
that's still one of the cons, though. That's a really big con for the thorium nuclear reactors, is this weapons proliferation. But yeah, perhaps less than the uranium-235. Perhaps the products are less, but yeah.
There's also that it's conducted in molten salt. So there was no high pressure water.
And I think that the fact that it's not a self-sustaining reaction, because about 10% of the output power goes into the laser spark plug. If you switch, like a car engine, if you switch the ignition off, then the reactor stops immediately, which is obviously a plus compared with conventional reactors.
Yes, one of the things I've read is that thorium reactors are supposed to be safer. They're inherently subcritical, so you can build a safe thorium reactor, whereas you always run the risk of a meltdown with a uranium reactor. Even though we now have 4th and 5th generation uranium reactors, which are safe enough, it's meant to be somehow more secure.
Yeah, I think it comes also down to like I think Cameron said about the liquid salt or the molten salt. I mean, if you turn it off, that salt will just become a solid and not pressurize the system and blow up. But again, I don't think that's the issue. I mean, the liquids or the molten salt thing is something that has been around since the 50s, 60s, and I think there's still also a lot of problems around that because it's aggressive and it really attacks your pipes and everything. So let's see if that. I mean, I'd be more than happy if something like that came rather sooner than later, because I think we need it. But let's see.
Is anyone working on thorium reactors? It has gone very quiet, as Scott said. I haven't heard anything about it in the last few years.
No, I don't know.
India was the big place really pushing it a few years ago, but yeah.
Yeah, I think India and the US have combined, and I think China's trying it as well.
Yeah, Google News doesn't show anything from the last couple of years. Something must
they know everything.
Yeah.
Yeah. I noticed that Patrick Hartley has joined us. So Patrick is here from CSIRO's missions, and the one based on the hydrogen industry. So welcome, Patrick. Maybe could you give us a little bit of an introduction to yourself and tell us a little bit about what you do and why hydrogen is the way to go?
After this conversation, I'm not so sure. Thanks everybody, and very out of my depth when it comes to nuclear energy, I have to say. So interested in the discussions, although I have heard of a Thor reactor. That's about as far as it goes. So thanks, Scott, for the invitation. I'm sorry I joined late. I got waylaid by my dinner, but I'm here now. Hopefully, looking forward to a chat about all this. So I lead our CSIRO's hydrogen industry mission, and I guess it's a new research initiative. It's part of a suite of missions that we're developing in CSIRO. We were lucky to be the first one to launch about 3 weeks ago, but we've been working on developing the mission for a long time. And really what it's about is us trying to sort of garner both the research that goes on in CSIRO, but also in the broader research community behind developing the hydrogen industry for Australia. And I guess it's probably by now fairly obvious that the hydrogen seems to be a big deal, because it seems to be more in the papers than we ever expected right now than certainly when we started putting the mission together about 18 months ago. It's an exciting time in hydrogen for sure. It's an exciting time in energy in general, with uncertainties everywhere and solutions somewhere. Very happy to join the conversation and tell you maybe some thoughts about what I know about, which is very much hydrogen, not much else. But background, I should say as well, I was a physical chemist, originally a microbiologist actually, but moved into physical chemistry and moved across basically into our energy business unit in CSIRO about 5 or 10 years ago, looking after a lot of petroleum research actually, but moved across into this hydrogen area in the last few years. That's me.
Can you give us a snapshot of how the hydrogen supply chain would work, assuming that we're in a situation where I think if we've got all of this sunlight and infrastructure and we're exporting hydrogen products all over the world, how does it work from a sort of a practical perspective?
Yeah, okay, no, I can certainly do that. I guess hydrogen has been used industrially for centuries, really. It's quite a traded commodity in some ways, at least locally, in usage in things like petroleum refining and semiconductor manufacture, ammonia production, things like that. So it's very much an industrial feedstock for those sorts of processes. But I guess the big desire now is to really broaden the use of hydrogen into different sectors. Things like transport, obviously people will be well familiar with fuel cells. So fuel cell development has been going since in earnest really since the Apollo program, and has obviously developed to the level where that technology for using hydrogen to produce electricity and drive things like cars and trucks has reached a level of maturity that makes it commercially viable. We just took delivery in CSIRO of a brand new fuel cell car that Toyota produced just a couple of weeks ago, and it basically just drives like an electric vehicle, but with the front end of that being driven by a hydrogen tank and a fuel cell. So smaller battery, hydrogen tanks allows you to basically refuel and regenerate that power much more quickly than you can if you're recharging a battery. So that's one of the I guess the niches for hydrogen in passenger vehicles. I guess in the Australian context, the story is all about having this tremendous amount of resources that we have and the potential to build a clean hydrogen industry. So there's no point in going to hydrogen unless you're going to decarbonize the processes that make it. And so one way of doing that, of course, is to use renewable electricity to split water, and the other way is to use a conventional hydrogen production process, for instance, steam methane reforming, where you essentially react methane catalytically to produce hydrogen from it with water. But that produces CO2, and so you have to do something with the CO2, and so that's where things like carbon capture and storage can be applied to abating the emissions from that well-established industrial process for producing hydrogen. So I guess the challenges in realizing that dream is, one, building the infrastructure to produce hydrogen at scale from renewable energy, and two, making sure that, that in the interim at least, that if you're producing hydrogen from fossil fuels, you really can sequester that CO2 or use that CO2 in a process that means that it's not just being emitted and you're back to square one with the issues we have with climate change, etc. So it's a lot about the cost of energy and renewable energy in particular, because as we know, renewable energy has got really, really cheap in the last 30 years, way cheaper than anyone really thought 10 or 20 years ago. And that means hydrogen comes into play because, of course, it does cost money to make hydrogen, and one of the biggest costs is that input energy cost. So we have lots of sunlight, we have lots of wind, we have lots of potential for producing renewable electricity, way more than we need as a country. And hydrogen offers us the pathway to actually convert that renewable energy into an exportable product. And that's probably the big prize for hydrogen is to really export that hydrogen globally. And that's game changing, really, if you think about it. The ability to move clean, carbon-free energy around the world in the same way that we now move, carbon dioxide emitting products around the world, or energy sources around the world, is really a huge leap forward in principle. But it's going to take time to build the stuff. It's going to take time. It's going to take time to get the costs of those processes down to the point where they become really economic and competitive with some of those cheaper, well-established but emitting processes. So lots of challenges, but lots of opportunity there as well.
So what sort of timescales are we talking about? You say one of the biggest challenges is the infrastructure, getting the infrastructure built. If you say this is going to be one of our top options for power or energy going forward, what do we need to do? How big is one of these plants that you're talking about?
Yeah.
How long would it take to build?
Yeah, so I mean, and as with renewable energy, I guess renewable hydrogen production is actually quite scalable. So you can do it. You can build out electrolysis capacity based on the amount of renewable energy that you can build to go with it. So so most of the electrolysis systems around the world now are sort of that 1 to 5 megawatt range, and that's going to produce you something of the order of 500 to a ton of hydrogen a day. So not much if you're trying to build enough for export, and so really the push is on to build that electrolysis capacity, build those devices to a much bigger capacity, 10, 50, 100 megawatts in scale, that allow you to produce the hydrogen really to the large amount that's required, both for export but for powering things like industrial processes that might you could displace natural gas usage in industrial processes using hydrogen. And so I guess there's a number of ways to answer that question. The way we sort of came up with, with Alan Finkel came up with, I guess, to describe that, is to think about, you take our current LNG industry as a benchmark, right, and you convert the amount of energy that we export annually as LNG into the amount of hydrogen that you need to export annually, and then you back calculate how much renewable energy you need to produce that. It's something like a terawatt. So the installed capacity of about a terawatt of renewable energy is needed to produce something of that scale. I'm not saying you need to get to that scale immediately, but that's the sort of build we're talking about to produce enough hydrogen for that particular market. So that's a lot of renewable energy compared to what we have now, and it's multiple times the size of our entire electricity market in Australia. So it's not going to happen in a hurry. That's not to say you shouldn't absolutely do it as fast as you can, but the investment in energy projects, the time it takes to fund energy projects, to build energy projects, et cetera, it's don't expect this to happen in the next 3 to 5 years. It'll be building organically, I think. And that's where I guess the fossil fuel pathway as a short-term fix is quite attractive, because you can produce a lot of hydrogen with only a very small number of projects using fossil fuel, but you have to do something with the emissions if you're going to really get that benefit. So we see that sort of CCS hydrogen as something that that can get us across the next 10 years and build the value chains, build the supply chains for hydrogen, and then you switch in the renewable energy as fast as you possibly can to decarbonize the whole process completely. So that's one view of the world. There are many others, there are many others. Many people say just forget it, just go straight to the green hydrogen, and that's great in principle, but it's a big ask to get that much renewable capacity into the system.
Patrick, a quick question about transport. I understand how small fuel cells work, small hydrogen fuel cells work, but if you have to transport large amounts of hydrogen for export, say, what's the weight ratio of hydrogen to the rest of the stuff in the fuel cell? And for those of us who still have fond memories of the Hindenburg, what do we say to them, and what can you tell us about how we transport this large amounts of hydrogen around the world?
Yeah, and that is in many ways probably the $64 billion question in many ways. So moving large amounts of hydrogen around the world needs a lot of work. And so there are a number of ways of doing it. Obviously, the energy density, the gravimetric energy density, that is the amount of energy per unit weight of hydrogen, is fantastic. It's really, really high. It's bigger than anything else because it's a very light molecule. So every molecule, has quite a bit of energy. So that's great if weight is what you care about. But if you care about volume, it's exactly the opposite story because it's such a low density gas. The amount of energy per unit volume is really, really small. Compared to something like a natural gas, let's say. And so what you have to do is figure out how can you cram enough hydrogen into a small volume in order to get to make it economic to move it around the world. And so there's a lot of work going on in the use of numbers of ways of doing this. Of course, you can take the simple approach and compress it, and you can compress up to the typical pressure in a hydrogen fuel cell passenger vehicle, at least, is around about 70 megapascals, 700 bar. So that's a serious pressure, to ram all that hydrogen into a volume that you can put on a car. If you other things you can do, so you can take that to the next logical step, which is actually to liquefy the hydrogen. So you cool it down to minus 253 degrees Celsius. Very cold, a lot of energy required to do that, and then you can liquefy it again and densify that hydrogen into a form that you can shift it around. And there's a big project here in Victoria looking at doing exactly that, where the Japanese are actually building ships that can at least demonstrate the movement of liquid hydrogen produced, in this case, from brown coal in the Victorian Latrobe Valley. And liquefied and loaded onto a ship, which will be actually arriving. I just discovered this just yesterday. The ship will be arriving, I think, in July. So there'll be a big song and dance around the arrival of that ship, which has been built by the Japanese, by Kawasaki Heavy Industry in Japan. And that's going to be arriving in Australia sometime, as I say, in July. It was originally supposed to be there to sort of demonstrate the process for the Tokyo Olympics. But we know that a few things got in the way of that, and so in a sense it may well be pretty close to the Tokyo Olympics, but not in the way that was anticipated. So liquid hydrogen, and then there's a whole other way of doing things, which of course is to convert that hydrogen into another form. So using chemistry to produce derivatives of hydrogen that you can either use directly as an energy carrier. Things like ammonia is a key carrier. You can put a lot of ammonia per unit volume. Sorry, a lot of hydrogen per unit volume into the ammonia molecule, and move ammonia around. Of course, it's much easier to transport than liquid hydrogen because it's a little bit of compression, a little bit of temperature, low temperature, to keep that ammonia in a form that you can put it on a ship and move it. But of course, you have the issue of the toxicity of ammonia. You're not necessarily going to be wanting to move ammonia around the country to refueling stations and things like that, because it's a pretty nasty toxic chemical. And there are other carriers that people are working on, things called liquid organic carriers, which are organic molecules, again, which you can just load up with hydrogen catalytically, and then you can catalytically unload them when you get to the destination and recover that hydrogen from them. So there's a whole class of chemical carriers that are being looked at in those ways. And of course, for many applications, a very active area of research has historically been the use of inorganic materials to store hydrogen. So things like metal hydrides, metal organic frameworks, all of these sorts of materials that again have easily loadable functional groups on them that you can start to load up with hydrogen and then recover at the destination. They all have their pros and cons. I think in the end there will be a whole range of these things that will be sort of adapted for certain purposes. But it is a real question. You know, how do you get the economics right for each of these different carriers to make it all work? So I think I honestly, you know, I would say that the storage and distribution of hydrogen is probably the single biggest technical challenge that's facing the industry right now. How do you make all that work from an economic, cost competitive, safety, all of those different issues that need to be resolved. So
yes, it sounds like manufacturing the hydrogen is the easiest part of the whole business.
I think that's probably true. Yeah, I mean, yeah. you know, when I look at our research portfolio, and we actually, you know, CSIRO just spun out an electrolyzer company just a couple of weeks ago, actually, called Endure, if you're interested, and you know, that's targeting a very specific electrolyzer size and scale for very specific applications. But you know, you pretty much say, well, electrolyzer research, you know, that's now a commodity or commercial property, and you let the industry do what it does and get the cost of that down, and focus on the other parts of the value chain, like the storage and distribution, where the technology is really needed. And of course, you know, from a market perspective, what we really need to do is figure out how we're going to use this hydrogen really effectively as well in a lot of the processes, like industrial processes I mentioned.
Yeah.
Okay. So is there any progress? Sorry, Warren, go ahead.
Oh, sorry, Patrick. I was going to ask, how far are we away from the $2 a kilo?
Yeah. So we actually just worked on the side that, you know, we do a lot of work with government, and for those of you who pay attention to the sort of government and energy policy, it's, you know, quite a drama, I guess, in many ways. But the government put out what was called the Low Emission Technology Statement around about September last year, that looked at the goals for hydrogen and the other 5 technology areas of the energy, what are called priority technologies for investment. We did some modelling for the government, which unfortunately we haven't been able to release yet because it's still sort of locked away in government. But I think it's fair to say what we could see with a realistic trajectory for production capacity, you know, those issues that I spoke about for both green hydrogen and also the use of fossil fuel hydrogen, we could see that, you know, the fossil fuel pathway with carbon capture and storage appears to be not far away, but it needs, you know, big investment to deploy the technology. You need to get the economies of scale through deployment to really bring those costs down. And so, you know, three or four, you know, large scale steam methane reforming plants with carbon capture and storage will get you there. But you know, projects like that still take 7 or 8 years to even start to build. You know, to go through the front-end engineering design, the final investment decision, actually the build, and then commissioning. These things all take time. So I think the short answer to the question is we think it's doable for fossil fuel-based hydrogen within the decade. For green hydrogen, it's probably a little bit, you know, it's a decade or a little bit more, depending on things like how the electricity cost tracks. You know, we're all expecting renewable energy costs to keep coming down. And so if that happens, then you can scale up the green hydrogen production. Then you can get there, but it's going to take time to build that stuff, like I said. So, you know, maybe 10 years.
What I was really asking is, what's the point at which we can take over you guys and produce cheaper hydrogen with fusion?
Great question. You know, it's yeah, as soon as you can do it at scale, absolutely, you're there. It's all about scale in this game. It's about producing enough hydrogen to build, you know, to have the demand to use that hydrogen, and then the production to meet the demand. It's the vicious circle there of supply and demand. But if you can get there with fusion, absolutely, please put me out of business.
Just to rewind a little bit, but before you came on, one of our ambitions is, you know, we're pushing a fusion or developing a fusion approach that creates electricity directly, and we were talking a little bit about how our minimum viable product is more likely to be a hydrogen electrolysis plant than it is going to be something that's going to be supply grid, just because our electronics are a bit easier.
Yeah, and that's you know, I think that's you know, and that talks to the point about you know, there's not just the large scale markets for hydrogen. You know, it's actually the, you know, the ability to see hydrogen as a distributed energy carrier, a distributed energy storage system in smaller applications. I think that's a huge opportunity, especially for the sorts of technologies that we can develop here in Australia. A lot of the big stuff is going to be done by Japan, by Germany, but you know, the opportunity to do stuff at a smaller scale, particularly where we have things like mine sites and remote communities here in Australia with technologies like that, absolutely huge opportunity. And that actually, you know, that Endure, that company that I spoke about is targeting that smaller end of town for those sorts of applications. Yeah, so I think you're right. I mean, you know, picking the scale that you can produce hydrogen at to power enough vehicles for a small community or a mine site. You know, it's all about matching the production with the demand that you have wherever you have it.
Yeah.
Patrick, can I ask a question? It might be a silly one, but is hydrogen part of the potential solution for the real cost of energy and steel making? Is that a viable way of generating lots and lots of heat locally? And yes. I guess part two of that for everyone else is coking coal. Are there any research projects that sort of get rid of that in the process? It's not quite energy related, but anyway.
Look, it's funny you say that, Bruce. It's actually, I was in Port Kembla on Monday this week. I actually had a trip away from Victoria. You know, it was like trying to leave, trying to run the gauntlet of COVID wherever I was. But I actually went up to Port Kembla to look at the BlueScope Steelworks up there, and it is. I'd never seen the steelworks before, and yeah, you know, I was talking about it tonight to somebody. It's so Victorian. The technology in the steelworks just appears so Victorian, and yeah. So one, you know, massive emitter. I mean, just, you know, you could see energy pouring out of this plant everywhere. Heat, CO2. You know, it was just thinking, wow, you know, this has got to be done. There's got to be a better way. And yeah. So there is a big interest in using hydrogen in direct reduction of iron ore, for instance. The DRI process is a you know, one of those ones that seems to have been worked on for a long time and seems to be close to being commercial, being investigated heavily in places like Scandinavia and Europe, and an opportunity to reduce some of those emissions, some of the heat aspects of the burning natural gas and coal. The coking process, yeah, that was something else. You know, they had these big coke ovens, and they basically, you know, they cook the coke, and they extract, you know, what is essentially a mixture. It looks a bit like syngas, a mixture of carbon monoxide and hydrogen, and they pipe that, and you know, you can power turbines using that gas, but it's pretty messy stuff. And so so electrifying those sorts of processes. You know, I'm not an expert on steel making, by the way, but you know, you need two things: you need heat and you need a carbon source. Or you need heat reduction and a carbon source to make steel, you know, the way you want it. So there's various ways of thinking about how you can incorporate hydrogen into some of those processes, but you're still going to need that carbon somewhere. So where you get that carbon is probably another really good scientific challenge to say, okay, can we use things like biomass? Can we use other carbon sources to, you know, we use hydrogen in combination with another carbon source, a renewable carbon source perhaps that can start to displace the really heavy fossil fuel usage in that process. I mean, massive emitters, really. And so there was if you want to read more about what's called green steel, then the Geraint Institute actually did a really nice piece of work on that just about maybe a year ago, maybe a bit less.
The Geraint Institute.
Geraint Institute, yeah. It's called the report is called It Starts with Steel. You know, and it's basically saying if you want to decarbonize heavy industry, then steel is a good place to start, and hydrogen and other technologies that can play a real role in that. You know, and so that you know, so people like BlueScope are thinking, okay, what does the future of our business look like in a carbon constrained world? So they're all looking at these sorts of solutions. Yeah, that sector is probably the single. You know, I think it's probably fairly obvious. It's really hard to abate.
Incidentally, if I can jump in, I know we've gone over time, but we recently responded to a discussion paper put out by the US Department of Energy, basically their fusion division. They were essentially trying to get more of the $1 trillion pie that is being divided up from the Biden administration at the moment, and they're trying to find new things that fusion can be used for. Our response was, you know, and a lot of that was, oh, we create heat. What can we use process heat for? And it was very nice for us to be able to say, we create electricity. We can produce hydrogen. That gives you steel, aluminium, fuel, ammonia. People don't realize that, you know, there's a lot more that you can do. Which is why the hydrogen strategy is great in my opinion.
Yeah, and that's one of the sort of favorite terms in the hydrogen world is this idea of sector coupling, where you can actually, you're coupling electricity generation with chemical synthesis, with heavy industry, with transport and the electricity industry. So it's a really, it's a very different paradigm to typically the way we talk about supply and demand. In energy. So yeah, absolutely. It's the diversity of opportunities is right there, and I think we haven't even scratched the surface of where else hydrogen could be used. I think that those are certainly big ones.
Scott, if I can jump in, are you monitoring the questions in the chat box, because there are people asking questions? And we're not answering them. So perhaps I could invite the people who are in the chat box asking questions. Why don't they turn their mics on and jump in and ask the question here, and then we'll all hear it, and then someone will respond to it.
Yeah, okay, I've got the chat. Shall I grab it?
Yeah, please do. Yeah.
There's a few hydrogen questions I can answer here. So transport around the world using a Zeppelin. Yeah, that's right. Well, that's the Hindenburg question right there. So I didn't answer the Hindenburg question. That's a great one. I mean, as an aside, one of the questions around hydrogen is, what's the social license to operate environment going to be like for hydrogen? Are there going to be questions that come up around safety? Is obviously the big one. And Peter Ashworth at University of Queensland did some studies on this, and asked the question, what do you think about the Hindenburg? And I'm afraid, Tibor, it turned out that it was only people in our age group that found that an issue. so younger people.
And perhaps historian.
So yeah, but you're right. I mean, safety is a huge one, right? I mean, people just absolutely rightly remember every bad story that's ever happened with hydrogen. So, but again, it's been used by industry for generations, and so industry, I guess the heavy industry in particular is quite experienced in using it. So and liquid fuels aren't that safe either. It's nothing with a high energy density is intrinsically a safe material to work with. So
sure.
So hydrogen is just one of those. But yeah, and the whole Hindenburg question. I mean, I have looked into this a bit, and there seems to be a pretty diverse set of views as to what actually caused that explosion and what it actually was. And there's a lot of theories that speak very much to the materials that were used in the construction of the balloon itself, rather than actually the hydrogen that caused the explosion, and at least led to the fire. And if you look at that video, that famous movie of the Hindenburg burning, it's not a hydrogen fire, because hydrogen burns incredibly fast. It doesn't burn; it goes bang. And you look at the sort of slow burn of that Zeppelin and think, oh, does that look like a hydrogen fire? I'm not so sure. So no definitive answers, and hydrogen certainly would have been involved there, but maybe the causes weren't just about the hydrogen, but about the materials it was made from.
Thank you for that, Patrick. I guess my question is about the electrolysis side. So we Australians are really good at transporting things around the world, fuels. We can do that. I don't really know how electrolysis works. It's not my area. Has there been any breakthroughs in the last 50 years, or are we still doing it the same way we used to?
Yeah, no. I mean, there have been. So I mean, probably the biggest leap was actually the development of a new form of electrolysis that actually had. I mean, it's not that recent. It's the Apollo program, but a process called alkaline electrolysis is literally, like your high school experiment where you put two electrodes in a solution of potassium hydroxide typically, and you electrolyze that solution and create hydrogen. It's pretty much that simple, and it's been done at industrial scale for at least 50 years. Probably more actually, and is if you want to make hydrogen at scale cheaply using electricity, that's a good way to do it. Again, as long as you have the cheap electricity to power that process. So places that pioneered that were had things like cheap hydroelectricity, which they didn't have anything to do with. So even countries like, I think Zimbabwe was a big producer of electrolyzed hydrogen using alkaline electrolysis. But the newer technology is called polymer electrolyte membrane or proton electrolyte membrane electrolysis, which is it's again an electrochemical process. It's a electrochemical process, but involves a rather more exotic stack structure to split, I guess, the reactants from the products. So water goes in one end. You use electricity to generate the potential across the membrane. Hydrogen and oxygen move across, or hydrogen moves across, and from the split water, and then you capture that hydrogen and also the oxygen that results from that process. And that's important as well, by the way. So it's a good way of producing hydrogen, but it's also a really good way of producing oxygen. So if you have demand for both of those materials, which places like wastewater treatment do, they need energy, they need oxygen for their processes, you get an additional value stream from doing that. I guess the technical advances around electrolysis are probably, I think, the fundamental process has been researched very extensively. Where we would see the big advantages or the big opportunities for research in that space is actually in the manufacture of those systems. So very expensive to produce, typically handmade. You can start imagining using things like 3D printing and rapid prototyping and all those new manufacturing technologies to produce those systems at scale more economically than they are now, because that's a big cost. The capital cost of electrolysis is a big part of the hydrogen cost equation. And lots of people looking at all manner of different electrochemical processes involving things like ammonia, directly producing ammonia, using ammonia as an electrochemical source for hydrogen. But yeah, the fundamental process is probably pretty well established, particularly in that PEM advance that's happened in the last few decades.
Go
on.
Yep, sorry.
Sure. Okay.
Yeah. So my question is, because you say this, that's what's my understanding was as well, that these plants are very expensive to make. So my question is always, what I don't understand about this green idea of hydrogen is like if you have 100 megawatts of nameplate renewables and you have 100 megawatts of electrolyzer, it'll almost never run at 100% capacity of the plant, right? So how is that dealt with in that whole strategy?
Yeah, well, and so when you're planning your capex on an energy project, you look at the capacity factor of whatever system you're putting in there, and yeah, you want to sweat the asset, and so you want to get that capacity factor as high as you possibly can, so there's numerous ways of answering the question. I guess it really is going to come down to, I think, to some really elegant, let's say, market manipulation is the wrong word, but looking at the market mechanics and trying to optimize when and where you may put your renewable energy into a grid or into a battery system or into some other system, and when and where you will actually harvest that hydrogen, harvest that electricity as hydrogen. One of the key things about hydrogen, of course, when you compare it to a battery, for instance, for storing electricity, whilst you have a big efficiency loss as you go from electricity to hydrogen. Obviously, it's about 60%, let's say, efficient, that process. But what you have when you have hydrogen is actually you have something that you can store for a very long time. In principle, at least, you can store it for a very long time, and so you can start answering questions around seasonal storage. Which batteries, of course, don't really do very well. Batteries are great for that sort of hours to days sort of storage, but obviously not for the longer term storage. So I think all of these things will be about like I say, working the market and clever business models that allow you to squeeze every dollar of value out of your energy and hydrogen, ultimately hydrogen as well. So,
but that's one of the things that drives up the cost of hydrogen, basically, because you cannot run your plant 100% all of the time.
Yeah. So you have and it's the same. You can't. Your renewable renewable energy plant, of course, doesn't produce electricity 100% of the time either, because it's if the wind's not blowing and the sun's not shining. So you have a capacity factor for the electricity production, and then you have another capacity factor on top of that for how much of that you can convert into hydrogen. So manipulating that equation and maximizing the yields.
But that comes when you said in the beginning we need about 1 terawatt of electrolyzing capacity. I mean, that means we need like 4 or 5 terawatts of renewables. I mean, this.
Well, I mean, we need to build up that renewable energy anyway, of course, just to provide the electricity for the country as well. So and then you start saying, well, are you doing everything behind the meter, or are you grid connected and somehow you're using spilled grid power to power that electricity, which may be even cheaper. So there's no straightforward answer, and it will come down to the individual business models. But yes, in principle, you're right. It's there's an efficiency. Any conversion you go through has an efficiency penalty associated with it.
Of course, yeah.
It reminds me a little bit of when I last visited Cornwall, where I grew up, and the transformation of the landscape was quite stark. There are solar panels and windmills everywhere. And as I drove down through the county, I was just I couldn't understand why the windmills weren't turning. It was a nice windy day, and then somebody explained it to me. My brother-in-law actually had bought he was a farmer, and instead of farming cows, he decided to farm photons, and he'd created a 1 megawatt panel in one of his paddocks. And he told me, you've got to pay for your feed line grid into the grid, and you pay by the size of the wire, and the places that had so a lot of places have wind and solar, and they can't, they've got a maximum number of amps they can pump in, and when it's sunny they turn the windmills off because it's just not economic to pay for a fatter cable into the grid.
But that's exactly, that's my point, coming back to the electrolyzing capacity. I mean, you have to somehow adjust it to what you can possibly take, but you cannot make it as large as, because these renewables kind of, the production is very, very spiky, and it's very sometimes it's I mean, it's not a very stable thing that you can have. So
they've introduced that charging tariff in Australia since March this year too, Scott.
Yes.
So Australian Energy Market Commission said, yep, we don't want an overload on our wires, so you now have to pay. So for all those people who decided that they would save money and make money by putting back to the grid, not anymore.
I mean, that's also a thing about price and value, right? I mean, the price is one thing, but what's the value of if every solar panel in Australia, for example, produces at the same time, the value goes, I mean, we have it here in Germany, the power prices go negative because there's so much supply that nobody wants it anymore. And that's also what happens when the windmills are being turned off, because that's the easiest thing. You just turn the blades and then they'll stop. But I mean, that's also an issue of, like, Patrick, like you said, market design. I mean, what do you do with all these oversupply? Because you cannot possibly build a few gigawatts of electrolyzing capacity just for that few hours in a month to run to take these spikes of excess power, basically.
And it's the same at the other end as well, right? So I mean, if you're building a renewable energy project and you need some firming gas to ensure that your supply doesn't drop out as a city or whatever else, then you have this dwindling. You're really putting a huge amount of money into the capex for a gas turbine that you're only going to use 10% of the time. It's it's really hard to justify, and like I say, the business models around this stuff are probably
this raises
really important question.
This raises the question of capacitance, doesn't it? I mean, we've got pumped hydro where we can store the surplus energy that we have on the grid and then reuse it when the supply is low. Can hydrogen play a role in that? You did talk about that, Patrick. You mentioned that you could use hydrogen to you could make hydrogen off the electricity, the surplus electricity grid, and then you could reuse it. But that would be, I presume from what you've said, much less efficient than something like pumped hydro. So if you've got an obliging mountain just next door, then that's a good thing. If you don't have one, then maybe hydrogen is one way of storing energy. It's all very well to produce lots of wind and solar, but if you need to store it when you've got it and then use it when you don't have it, then that becomes an economic consideration. It becomes really the major player in the entire electricity system.
Yeah, no, absolutely right. The storage is key. You know, we talk about electrolyzers being used actually as a flexible load on the grid to sort of iron out some of those fluctuations, and you know, and I think, you know, so yes, hydrogen obviously you can store it. It doesn't, you know, doesn't run out. It doesn't go off, as it were, as you store it. So if you can store it at large scale, then you can start to think about, you know, models where you have you know when the sun's shining and everything else, you produce hydrogen, and then you put it through a fuel cell to regenerate the electricity when you need it, and at night or whatever else, or whenever the renewable.
What are the inefficiencies involved in that?
Yeah, well, exactly. So 50, you know, it's 50-60% each way. So
okay, all right. So it's pretty big.
Yeah. I mean, they're quite efficient. You know, for what they are, they're efficient processes. But you know, if you can avoid any of those conversion steps, then you should. You know, so. Sure. You know, we always say, you know, if you've got a need for electricity, you know, make the electricity and use it. Don't put it through the hydrogen pathway if you don't need to. But in places where you want to store it for longer or use it for something else like powering vehicles, then hydrogen makes sense in those things. And and for instance, some of the stuff we were actually looking at in CSIRO as well is looking at how we can store hydrogen at large scale. I've talked about chemical carriers, but another way of storing hydrogen as hydrogen is actually to store it underground, believe it or not. So there are countries in the world where storage resources based on salt caverns are actually being used now for storing hydrogen at you know, moderate pressures underground at large scale, and so we can start thinking about repurposing, I guess, some of our oil and gas fields or depleted oil and gas fields for storing hydrogen potentially around the country. So so we're starting to trying to look at some of the properties of those reservoirs that might make them very good for storing hydrogen at large scale. For example,
we are rapidly approaching half past. Let's take Bruce is itching to ask a question, so let's take Bruce's as the last one.
All these comments about capacity in Australia and the challenges of building enough capacity here. It made me think of these exports. People talk about shipping electricity from Australia to Asia, you know, using superconductor cables and this sort of thing. Is that completely off the planet and out of the question, given the challenges we're going to have producing capacity at home and producing enough capacity for this electrolysis and all the rest of it? Have any of you heard of those sort of ideas of using high temperature superconducting cables to sort of export up to Indonesia because we've got so much solar real estate? But surely we'll be using it all here.
No. I mean, you know, we have so much electricity generation potential and a relatively small population here that we have in principle plenty of energy to supply the rest of the world in whatever form. And so, you know, I think companies like Sun Cable is a company that's been looking at that. Moving electricity cable. I honestly don't know what the technical challenges are there. I'm assuming losses must be a problem, but don't quote me. But you know, at the same time, we're a long way away from many of these countries. So I'm certain if you're you know, in a dense populous part of the world like Europe, then moving electrons around by wires makes perfect sense. But when you're a long way away from some of your markets in Southeast Asia, for instance, you know, beyond Indonesia, but further north even, like Japan and Korea, then moving hydrogen is certainly something they're thinking very hard about.
I guess the core of this is what you just said there about you believe we've got massive overcapacity for our population. So that's really the core, isn't it?
Exactly.
In principle, we could do it. Yeah,
absolutely. I mean, the amount of you know, insulation that hits that planet. I don't know if you spoke about this earlier on, maybe you did, but it hits Australia. It's massive. And so the potential to produce the energy is not the problem. It's building the gear that will actually do that, and then figuring out how you move it around.
I mean, there was a project in Europe. They wanted to import solar energy from the North African countries, and they wanted to use high voltage DC cables to transport, but it died like 5 years ago. So I think all these long cable things, I mean, underground superconducting cables, what if something goes wrong with it, you have to go down a few thousand meters to repair something. I'm not sure if that's reliable enough for anyone to do. I mean,
yeah, I don't know what the history of that. I mean, I'd certainly heard about that project. I also heard
it's called Desertec. You can look it up. It was a massive consortium of Siemens and all these big companies, but I mean, it died. I mean, also for political issues in the northern African countries, right? I mean, then there was this Arabic Spring that every country was a bit destabilized, and with the war in Libya, and so I mean, that's also part of it. But I think not an industrial country can really rely on these regions to provide for their stable power supply.
And that's right. And we talk about Australia being having that low sovereign risk that means that we're a bit more, maybe a bit easier to deal with and a bit more reliable in some.
In that sense, yes.
Bruce, with my material scientist hat on, a long distance superconducting cable is, that is off the planet. It's, big breakthroughs needed for that, and a lot of research has gone into trying.
And bear in mind, I think when you say high temperature superconductors, it's still like minus 100 or minus, how much is it, Warren?
Yeah, minus 70.
Still sheathed in liquid helium.
Minus 200. Yeah.
Unless you've got high pressure.
We're going to have to call it a day, I'm afraid. I think this is a topic that we're going to have to come back and revisit again, because there were lots of topics that around storage and the grids that we didn't get to. So it's been a wonderful conversation. Thank you to our special guests, Warren and Patrick, and also Tibor, Kirilee, and Geraint, our regulars. I will launch, as you leave, the final poll to see whether we've changed your mind at all. Hydrogen's not on there because it's not a source.
Very good.
Yes,
we haven't quite decided what topic to cover next month. So if you'd like to make a suggestion, feel free to do that in the comments before you leave.
I think this is a good time to suggest it. This has obviously generated so much interest, and there's so much more to say. We really only touched the surface of the question of power. Why don't we continue this next time?
Okay. We could. We didn't even get on to nuclear fission yet.
There's so much more to do. I think this can go for quite some time yet. In fact, I think next time we should have a session that goes for 6 hours instead of.
Oh goodness!
All right, let's do that.
You're gonna need a wine sponsor, Scott.
Yeah,
I know. I might already have one. Thank you, everyone, for. I don't think we've made much, or I can end the polling and share it. I'm looking at it, and I'm
all of the above,
Scott. You can't see it. So thank you very much, everyone. I really appreciate your time. Sorry we've gone a little bit over, but I was finding it very difficult to interject into that conversation. Let's convene again this time next month and continue the conversation. Thank you very much, everyone, and